All right, so now let's start exam 2 review part 2, doing some more example problems related with the lecture material on quantum mechanics, starting with the introduction to quantum mechanics all the way up through mini electron atoms. All right, so for the very first question here, we'll look at some simple multiple choice questions, right? So I have a total wave function, right, that's written combination psi2, psi4 here, where psi2 and psi4 are eigenfunctions of the harmonic oscillator system, okay, right, where the 2 and 4 are indicating that they're the quantum number equal to 2 and quantum number equal to 4 wave functions, right, for the system. And so the question is, what is the expectation value of the energy, or the average value of the energy, is another way to write it, of this total wave function, okay? So the expectation value of the energy, right, if you want to compute it, you would solve this integral of psi star total with the Hamiltonian psi total, right? And I'm putting d tau here, right, integrating over all space, right? I try to solve this integral, right? Not something we want to do, but what we can notice is that the wave function is a linear combination of eigenfunctions, psi2 and psi4. So this expectation value, this eigenvalue, simplifies greatly because psi2 and psi4 are orthogonal, right? Integral of psi2, psi4 is equal to 0. And because of that, this simplifies greatly. And because they're eigenvalues of the Hamiltonian, I know that the Hamiltonian acting on psi2 gives me back E2 times psi2, which E2 is just 1/2 of 2 plus 1. Oh, I always forget the energy for the particle, or the simple harmonic oscillator here, right? It is the quantum number V plus 1/2, right, times h bar omega, right? And let's, instead of doing V here, let's plug in the actual number, right? It's just 2, okay? So E2, right, is just equal to 5/2 h bar omega, and then E4 is just equal to 9/2 h bar omega. Okay, so then the total, right, what this ends up being here, right, then the expectation value of the energy is just going to be related to the probability of being in state 2 times its energy, which the probability of being in state 2 is its coefficient squared. Okay, so 5/8 times its energy, which is 5/2 h bar omega, plus then 3/8 times the energy of psi4, which is 9/2 h bar omega. Okay, and so when you simplify this down, you'll end up getting d here 13/4 times h bar omega. I believe so. Let's see, 25. Yeah. Okay. All right, for this next question, looking at how the change in bond distance affects the energy level spacings of rotation. Okay. So the energy for rotation, right, is just related to L times L plus 1, h bar squared over 2I, right? We know I is related to mu r squared, where mu is the reduced mass, which happens to be 1/2 times the mass of O2 for this problem. Not too relevant. The main thing here is that we're saying, right, in the problem we're told that the new spacing, the new bond distance, right, is equal to 1.3 times the old bond distance, okay? And so that means that I new is equal to, right, mu r new squared, which equals mu times 1.3 squared times r old squared, okay? which then tells us that I new is equal to 1.3 squared times I old. Okay. So, right, and so the energy, right, is, right, that the energy spacing is related to something like EL plus 1 minus EL, right, which is going to have some dependence. I mean, if you work it out, it's 2 times L plus 1 H bar squared divided by 2I, okay? And so this still has this 1 over I dependence. So if I increases by a factor of 1.3 squared, that means that delta E nu, right, of L has to decrease by a factor of 1.3 squared compared to delta E old here with L. And so you plug that in and you get D here.